When you look at a really complex math function, have you ever wondered what its actual shape is? What its story is? Well, today, we're not just going to find answers. We're going to become detectives. We're going to figure out how to sketch the entire story of a curve using nothing but its equation and a few really powerful clues from calculus. So let's get right into our first piece of evidence. So this right here, this is our mystery. I mean, look at it. It looks pretty wild, right? A mess of curves flying off towards infinity. But here's the cool part. By the end of this, you'll know exactly how to break this function down and draw this exact picture from scratch. No calculator needed. We're just going to follow the clues. All right, so our first clue, and honestly the most important one, comes from the first derivative. The best way to think about it is like a compass for our function. At any point on that curve, the first derivative tells us which way we're headed. Are we going uphill, downhill, or are we on a flat spot? And the rule here is just so simple and elegant. If the derivative's value, which is just the slope, is positive, our function is increasing. It's going up. If that value is negative, the function is decreasing. It's going down. It's literally that direct. All we have to do is ask, is the slope positive or negative? And we know if our curve is climbing or falling. Okay, so if the derivative tells us the direction, then the most exciting parts of the story have to be where that direction changes, right? The moments where we stop climbing a hill and start heading back down into a valley. That leads us right to our next clue. And these special locations, we call them critical points. These are the absolute peaks of our hills and the very bottoms of our valleys, where for just a moment, the slope is totally flat. It's zero. Finding these is like a detective finding key locations in a mystery, because here's the deal. Any local maximum or minimum has to happen at one of these spots. And here's how we can tell what we found. If the slope was positive before our critical point, and then it's negative after, well, we just went over a hill. And if it was negative before and positive after, we just passed through a valley. It's all about watching how the direction changes right around that flat spot. Okay, so we know if we're going up or down, but how are we going up or down? Is the path curving upwards, kind of like the inside of a bowl, or is it curving downwards, like the top of a dome? To figure that out, we need our second clue, the second derivative. This whole idea is called concavity, and honestly, it's super intuitive. If the curve could hold water, like a cup, we call it concave up. If it would spill water, like a frown, we call it concave down. This simple idea tells us everything about the bendiness of our graph. And just like with the first derivative, the sign of the second derivative gives us the whole story. A positive second derivative means our curve is bending upwards. It's concave up. A negative second derivative? You guessed it. It's bending downwards. Concave down. Simple as that. So what about that exact spot where the curve switches from being a cup to a frown, or the other way around? Well, that has a name too. It's called an inflection point. It's the point where the fundamental bend of the curve just flips, and we find it by looking for where that second derivative changes its sign. All right, our final set of clues isn't so much about the curve itself, but about the invisible lines that kind of contain it. These are called asymptotes, and they act like guardrails, They guide the shape of our function, especially when it starts heading way out towards infinity. So you've got vertical asymptotes where the function just blows up to infinity. That usually happens where a denominator hits zero. You've got horizontal asymptotes that tell us what the function is doing way, way out on the edges of the graph. And sometimes you even get these cool diagonal ones called slant asymptotes. Together, these lines form the skeleton of our graph. All right, team, we have gathered all of our detective tools. We've got the first derivative for direction, the second for the bend, and asymptotes for the boundaries. It is officially time to go back to our original mystery and crack this case wide open. Every good detective needs a process, a game plan, and this is ours. We're going to follow these 6 steps, nice and methodically. Each piece of information is going to build on the last until suddenly the full picture of the graph just emerges right in front of us. Okay, so we're not going to drag you through all the algebra, but after applying all our tests to that function, this is the case file we've put together. Let's look at the evidence. We know the curve only crosses the axes right at the origin, 0, 0. We've got these vertical boundaries at x equals -2 and 2, and a horizontal one right on the x-axis. And get this, the function is always decreasing, but it flips its concavity right at the origin. With all this evidence, we are ready to sketch this thing. Okay, first things first.
We have to draw the skeleton. That's the horizontal asymptote at y equals 0, and our two vertical ones at x equals -2 and +2. We'll also pop our one known point on there, the intercept at 0, 0. This framework right here carves up our canvas into a few different regions we need to solve.
And now we just fill it in, one section at a time. Let's see. To the right of x equals 2, our case file says the curve has to be decreasing and concave up. Well, that can only look one way. Between -2 and 2, it's got to pass through 0, 0. It's concave up on the left of that and concave down on the right, but it's always decreasing. And finally, to the left of -2, it's got to be decreasing and concave down. See? We're just connecting the dots using our clues. And just like that, there it is. The complete picture. The mystery is solved. By systematically putting all of our clues together, we've revealed the true shape, the true story of this function. Every single twist and turn makes perfect sense now. And that really gets to the heart of it, doesn't it? We're not just plugging in numbers here. We are learning a language that lets us read the narrative that's hidden inside a function, all its peaks, its valleys, its bends, and its boundaries. And you know, this kind of detective work isn't just for graphing functions. This way of thinking, of breaking down a super complex system into its basic behaviors, is an incredibly powerful tool for understanding the world. It really makes you wonder, what other hidden stories are just waiting out there in the math all around us?